All right. You can start, please.
Okay, sir. So good afternoon, everyone. My name is Olade, and I'll be presenting for Group 5 for the course CSC 704. So these are my group members' name. Now we start with interpolation. For our course, we are talking about interpolation and methods of interpolation. So what is interpolation? Interpolation is a method for estimating the value of a function from known values of the function. It is also used for deriving a simple function from given discrete data sets, such that the function pipes through the provided data points. Also, we can say interpolation is a process for determining unknown values that lies between known data points. So what do I mean from this definition? We all know our graph. I think we are all familiar with the graph. And this graph is a straight line graph constructed from the straight line equation, which is generally known as y is equals to ax plus b. So for most time, anytime we are asked to plot our graph, we are always given our function f of s to either be a straight line equation or a quadratic equation.
Excuse me, please. Can you make your screen bigger? Yes.
Sure.
It's a bit one-sided. Okay.
Okay. Yeah, so like I was saying, we all know the graph, our x and y graph. And from our graph, we are sometimes asked to plot a graph, given a range of x, we get the value of the y, then we plot our graph. So most of the time, we are always given a function in which we use to calculate the corresponding value of y for at any point of x. So our graph here is the graph of our x and y, where this part is the y-axis and this is the x-axis. For this range of x, we have the corresponding y value. So most of the times we are given a function, but at times in mathematics, we are always given a collection of other pair of numbers without our function being explicitly stated. And we are always asked to find like the corresponding value of y at a point in x. So for this graph, we are given our x-axis to be 0, then the corresponding value of y, we can see it's 1. So from here, we can, for this graph, although we're not given, the function was not explicitly stated, but they were able to graph them. They're able to bring out the graph from our x and y data. So interpolation is the process of determining the unknown values that lie between two known data points. This is a data point. The circle dot is a data point on the graph. This is another data point on the graph. So in the process of interpolation, we might be given to find the mid value between these two data points. The process of determining the mid value between these two data points is what we call interpolation. As we continue, we get more understanding of it. So here we are given an example. So this example, we are given a function f of s, which is equals to 4s raised to the power 3 minus 3s squared plus 7. Now, the values of the dependent variable of function f of s corresponding to the value of the independent variable x can be found by direct substitution. Here, our x ranges from 0 up to 9. 0 and 9 excluded from the range. So for here, if we are asked to get the corresponding value of our function f of s, when our s is equals to 1, we can compute it by direct substitution. We just substitute the value of our x into this equation, and we are able to get the corresponding value of our f of x, which is also referred to as the y-axis. Here, we substitute our s equals to 1 into the function. We're able to get our f of 1 to be equals to 4 raised to the power 4 times 1 raised to the power 3 minus 3 times 1 raised to the power 2 plus 7. Computing this equation, we derive our f of s to be equals to 8. So we can say at s is equals to 1, our y, which is equals to our f of s, is equals to 8. So by direct substitution, we are able to determine the range of our function f of s from the given equation, But sometimes a function is not always defined as the above equation. Sometimes we are just given a collection of other pair of numbers. So how do we find the corresponding value of the dependent variable? So sometimes we might not be given a function f of s as explicitly stated here as 4s raised to the power 3 minus 3s squared plus 7. Sometimes we are just given a table with our x and y values, and we are asked to determine another value of x that lies within that range. To get sometimes we are just given the value of x and we are asked to determine the value of y that lies within that range. So how do we calculate that? That's where interpolation comes in. For interpolation, the function is not always explicitly stated. We are just given a set of data points, and from there we are asked to compute the corresponding value of our y when our s is explicitly stated. So an example is going to be shown. So for this example here, we are given just a table of our x and y values. So we have for x equals to 1, we have our y to be equals to 4. Our s is equals to 2, we have our y to be equals to 14, and so on. So here we are asked to determine the function of 2.5 when our x is equals to 2.5. So here we are asked to determine the corresponding value of our y if our x is equals to 2.5. For the earlier example, our f of x was explicitly stated, that means our f of s was given. But for this example, our f of s was not given. So how do we estimate the corresponding value of our y? This is where interpolation comes in. Looking at this table, this data can be calculated by estimation. So we know that the midpoint between 1 and 2 is 1.5. You can say the midpoint between 2 and 3 is 2.5. The midpoint between 3 and 4 is 3.5. So from there, if you are asked to find our function, the corresponding value of our y when our s is equals to 2.5, you can just find the average of 3 and 2. Here we get it as our s to be equals to 2.5. And by estimation, we can say that combining the function, combining the value of our y at s is equals to 2 and of our y at s is equals to 3 divided by 2, we can estimate that our function s is equals to 2.5, the corresponding value of y will be 27. So this estimation process is what we call interpolation. So there are several methods that has been stated for interpolating a value of a function. So part of this method is what we'll be looking at. So here we'll be talking about polynomial interpolation. So we are considered giving a set of data points, xi, yi, where our I ranges from 0 to 9, certifying that the relation y is equals to function f of s. Here the f of s is not explicitly stated. That means we don't know the equation of function of fs. It is required that we find a simpler function, let's say theta of s, such that our f of s and that theta of s are great at a set of tabulated points. This process is called interpolation, and our theta of here we assume that our theta of s is a polynomial. That process is what we call polynomial interpolation. And our theta of s is called the interpolating polynomial. So in this section, we'll be considering the approximation of any unknown function by the means of polynomial. So what that means is sometimes our f of s is not explicitly stated. So we try to find another function, let's say theta of
Yeah, is a fellowship presenting? It appears I can't hear him again. Yeah, can everybody hear him?
No, I can't
No.
either.
You can't?
I can't
Okay,
hear
I
you.
can hear you now.
Yeah, back now.
Oh, maybe it's the internet. Because it might be my internet. So, like I was saying, for polynomial interpolation, here we consider giving a set of data points, xi, yi, where our I ranges from 0 to n. certifying that our y is equals to function f of s. And most time, our function f of s is not explicitly stated. That means the function f of s is unknown. It is required that we find another function, let's say theta of s, such that our f of s and our theta of s agreed at the set of tabulated points. This process is what we call interpolation. Here we are trying to determine another function, theta of s, in which by the time we define it, and we use to calculate the value of our y, it will be so close to the real function f of s. So here we say our theta of s, we assume our theta of s to be a polynomial. A polynomial can be a polynomial of any degree, of degree 2, of degree 1, of degree 3. So, and that theta of s, you also call it the interpolated polynomial. So as we go on, we'll be considering the approximation of that unknown function by the means of polynomial. This brings us to part of the method for interpolation is the linear piecewise interpolation. So for the linear piecewise interpolation, we consider be given a set of data points, xi, yi, where our I ranges from 0 to n. We say our xi, which is also the interpolated polynomial as I earlier stated, is for our linear spline of degree 1 is defined in the interval stated above. So our xi represents a straight line joining the points xi minus 1 and yi minus 1 and xi, yi. Here we can say our xi is a straight line equation, y is equals to as plus b. So let me explain what the linear piecewise interpolation means by the means of the graph. So let's say we are given a collection of other points of numbers. So we have our x, y to be 0, 1. At this point, we have our s, y to be 1, 5. Also at this point, we can estimate our s, y to be 2, 5. Let's say we are not connecting these dots together, and we are asked to find the value of x between the points 0 and 1. Let's say we are asked to find the value of s, which is equals to 0.9. For us to estimate the value of y when our s is equals to 0.9, we can decide to draw a straight line to connect these 2 points together. That straight line, and we know that the function of a straight line, the equation for a straight line is y is equals to as plus b. So we are taking that straight line equation to be our interpolating polynomial. We are saying that using that straight line equation, we can estimate the rest of the value of our y using that interpolated, using our straight line equation. Because if you are to find the midpoint, let's say a value of x when our s is equals to 0.5 between the points 0 and 1 on the x-axis. Since our function is not explicitly stated and we don't know the function used to derive this graph, we can just connect these two dots together, and this straight line used to connect the two nodes or points together is what we call the straight line equation. And we substitute it to be our interpolated polynomial. The function that when we solve for it is going to give us a closed value as the real function used to draw this particular graph. So our listwise interpolating function is given as our xi of s, which is equals to our yi minus 1 plus our mi into brackets x minus si minus 1, which is also a straight line equation. Y is equals to as plus b. Here, our m is the slope of the line. And the formula for the slope of the line is given as y minus 1 divided by x minus xi minus 1. So an example we shed more light on is, so here we are given a set of data points certifying that the function y is equals to f of x. We are now asked to determine the approximate value of our y when our s is equals to 2.5 using the linear spline method. So we are given a set of data points. At s is equals to 1, our y is equals to minus 8. At s is equals to 2, our y is equals to minus 1. At s is equals to 3, our y is equals to 18. Here we are asked to find the value of y when our s is equals to 2.5. And our function f of s is not explicitly stated. So we are going to use we are asked to use the linear split method. And this linear split method function is giving us our xi of s, which is equal to our yi minus 1 plus our mi into bracket xi into bracket x minus xi minus 1, which is basically the straight line equation. So here to solve this, to get the value of our x is equal to 2.5 using the linear split method, we know that to be able to determine the value of our f of x when our s is equal to 2.5 using the linear split method, we are given that our linear split equation to be equal to our xi of s, which is equal to our yi minus 1 plus our yi minus 1 divided by xi minus xi minus 1 into bracket x minus xi minus 1. Here we know that our 2.5, the value of s is lying between the points 2 and 3. And our I is the number of straight line connecting the nodes. Our I is defined as the nodes. So what do we call the nodes? If you look at this graph, this is the first node. This is another node. This is another node. So if you can see my mouse, this is the first node. This is the second node. This is the third node. Our I is defined as the nodes, the node points connecting the. Our I is defined as the node point between. Our I is defined as the number of nodes. So, and since our x value is lying between two nodes, our I is equals to 2. So our I is just the number of nodes between two midpoints. So from our linear split method, we can say our I is equals to 2. So substituting our I is equals to 2 into the equation above, you can say our S2 of S will now be equals to y is equals to 2, y equals to y2 minus 1 plus our y2 minus y2 minus 1 divided by S2 minus 1 into bracket x minus S2 minus 1, which we have as our next equation. By the time we solve for this equation, we have our S2 of S to be equals to y of 1 plus y2 minus y1 S2 minus S1 into bracket x minus S1. And this equation looks closely like the straight line equation. So from our table, we can determine the value of our y1, y2, x1, s2, and our x. From our data point, we know that the value of our y1 is given as minus 1, which is the value of our y at the first node, and our s1 is given as 2. Our y2 is given as 18, and our s2 is given as 3. Our s is which is equal to 2.5, is the value is the independent variable in which we are trying to use to find the function y is equal to f of s. Now substituting all this into this equation S2 of s, we can now have that our S2 of s is equal to minus 1 plus 18 minus 1 divided by our 3 minus 2 into bracket 2.5 minus 2. Solving for this equation, we can say that using the linear split method, the value of our y at our s is equal to 2.5 is approximately equals to 8.5. It is not equals to 8.5 because we know that our linear split method is going to give us an approximate value, not the exact value, since we don't know beforehand the equation used to derive those set of data. So we can say using this linear split method, the corresponding value of our y at s is equals to 2.5 is approximately equals to 8.5. So that is a basic example of using the linear split method to estimate the value of a function, of an unknown function at a point using the linear split method. Next, we go to the cubic spline interpolation. The most common piecewise polynomial approximation uses the cubic polynomial between each successive pair of nodes, and such method is called the cubic spline interpolation. Now, a general cubic polynomial involves 4 constants. So there is sufficient flexibility in the cubic spline procedure to ensure that the interpolant not only is continuous differentiably on the interval, but also has a continuous second derivative. The construction of the cubic spline does not, however, assume that the derivative of our interpolant agree with those of the function it is approximating even at the nodes. So let me try to explain what the cubic spline interpolation is. So you will see that for this graph, our line is more smoother than when we are trying to use the linear piecewise interpolation method. For the linear piecewise interpolation method, we just connect nodes together. So, but the advantage of the cubic spline interpolation method to our linear piecewise interpolation method is that we are able to achieve a smoother trend. So let's say most of us, we have seen graphs and we've seen lines, and these lines are sometimes used to make predictions. Let's say this is like a weather app now. We can say that at a point of S0, this is the corresponding value of our Y. So our cubic spline give us more approximate value,
Kind of.
approximate trend. Hello, sir.
Engineer,
Hello.
We can
Hello?
hear you. We are with you. We are with you.
Okay. So that is the
I think somebody was having some issues. Yeah, you can continue.
Okay, sir. So our cubic spline interpolation gives us a better curve on our line than the linear piecewise interpolation. So for our cubic spline here, we can see we are still having a straight line connecting the nodes, but the straight line is much more smoother than our cubic spline, than our linear piecewise interpolation, which gives us a much more approximate value to the real function f of x. So for our cubic spline, we are given a function f divided on an interval and a set of nodes a, which is equals to the s naught, our starting node, and our s of n, which is equals to b, is our ending node. So for a cubic spline interpolant, x of function f is set to satisfy the following condition: that our f of s is a cubic polynomial. That means it's a polynomial of degree 3, and it cannot be greater than degree 3. Our cubic spline, the polynomial function or the interpolant function s is always of degree 3. It cannot be greater than degree 3. We have it that a part of also the condition is that our interpolant function must be equals to our exact function f of s at range at each set of nodes. The first derivative of our interpolant function must be continuous, and the second derivative of our interpolant function must be continuous. What I mean by continuous is that by the time we find the derivative of the first function of the function and the second derivative of the function, and we plot the given value of our x and y, the graph must also be connected. There must not be discontinuity. That means it's not that we have our node going like this, then we cannot connect it to the other point. So what we mean that the first derivative and second derivative must be continuous is that our graph does not break after we try to plot the graph of the first and second derivative. These are the conditions for the cubic spline interpolation method. Next we go to the least square approximation. An important area in approximation is the problem of fitting a curve to experimental data. Most time we collect data from different sources and then we try to plot the graph of the data. And most time we just have nodes on our graph that are not connected. So what the least square approximation method help us to create a trend out of our data, out of an experimental data, and avoid what we know as the measurement error or deviation error. So it brings about what we call data fitting. So let me explain through this graph. Now we can see the graph. Let's say this is a graph of, we are trying to estimate the number of the infectious rate of, let's say, cholera in let's say in Lagos. And after we collect our data, we have it that this graph, there are different nodes. And this node, there's no how we can connect them all together. I will be able to get a proper trend to make a proper analysis. So what the least square approximation does for us is that it gives us a way whereby we can form a straight line to be able to get a proper trend out of this data points we have on the graph. So what it does is to define the correct straight line, as the line minimizes the sum of squares of the distance between the data point and the line. So the least square approximation method helps us to create a better trend for experimental data, like data scattered abroad on a graph. What this square approximation method does is to help us to create a better trend of our data, help us to connect the nodes that are necessary, the nodes that gives us less error from all other nodes. So the least squares approximation method says that the curve that best fits a given set of observations is said to be a curve having a minimum sum of squared residual. When I mean residual, we mean deviation of error from the given data point. So let's assume you are given a data point x1, y1 up to sn, yn, in which our x are the independent variables and our y are the dependent variables. And we suppose that our function f of s is the fitting curve, and our d represent the error or deviation from each given point. We can calculate our deviation error at each point as d1 is equals to y1 minus f of x1, d1 is equals to y2 minus f of x2. For each node in the graph, you can calculate the deviation error as using this formula. So the least square approximation method explains that the curve that best fits is represented by the property that the sum of all squares of deviation from the given value must be minimum. So what that means is, using the least square method, we find the deviation for each of our nodes, and that means the error using that earlier formula we saw. And the how we now connect is the node is we calculate the sum of all nodes in which the deviation error is at minimum. So the least square method helps us to calculate the sum of all nodes in which the deviation method are the error at connecting each node will be minimum. That helps us to create a better trend out of an experimental data. So our least square formula, our least square method is giving us our y is equals to as plus b, because our least square method helps us to just create a straight line. We are connecting the node on a straight line. They have a straight line trend. So our least square method is giving us our y is equals to a plus bs. And the normal equation for our y is different from that of the linear piecewise interpolant method we saw earlier. Here, our a normal equation for our a is given as the sum of our y values equals to our n, which is the number of nodes, times a plus b, is sum of our s values. And the normal equation for b is given as the sum of our x, y, which is equals to our a, the sum of our s plus b, the sum of our s squared. Solving these two normal equations will be able to help us get the required trend line equation for our a, for our y is equals to as plus b. So an example we shed more light to the least square line method. So here we are given a time series data, giving us our xi, our s range from 8, 3, 2, 10, 11 up to 8, and our corresponding value of the y on this data. We are asked to use the least square method to determine the equation of line of best fit for this data. That means to plot the line, we are asked to use the least square method to determine the equation. Here we just have series of data, but how do we connect each node? Which node are we to connect that will give us the minimum, that will give us the proper trend? We are asked to use the least square method to determine the equation of the line of best fit for the data. So the least square line is given as our y equals to a plus bs. Now, in order to determine our a and b coefficients to plot the line, we know for the normal equation for a, we have it as the summation of our y, which is equals to na plus b summation of our s. And the normal equation for our b is given as the summation of x, the summation of the product of xy, which is equals to a, the summation of s plus b summation of s squared. Looking at this table, we are able to derive the summation of our s to be 62, the summation of our y to be 72, the summation of our s squared to be 468, and the summation of our sy to be 503. Substituting these values into the above equation, we can see that from equation 1.0, that the summation of our y is given as our na plus b summation of our s. And from this table, yes, sir.
Yes, how did you generate all these values for x and values for y?
So it's given from this time series data. These are the data for our x, these are the data for our y. So we just get it in a table to be able to solve. These are the value of our x, these are the value of our y. So this is the value of all x squared. So the value of x squared here is given as the value of 8 squared or the value of 3 squared. Since our summation, we are trying to sum the value of all our x squared and the value of our y. That's why we have it like this. So it makes more sense.
You have the first x to be 8, then y to be 4, x squared 64 days. Now, can we see the other table, the previous table?
The previous table we have.
Yeah, you have x to be equals to this, right?
8, yes, and y is equals to 4, s is equals to 3, y is equals to 12, s is equals to 2, y is equals to 1. So we just kept that. We just kept that in this table at this straight line. Then we are now using it to.
Is it this the straight line on x?
The straight line on x are the value of our x.
Oh, okay.
The straight line of y are the values of our y. So our s squared is now given as 64. Our s squared and our x and y is given as times 4, which is given as 32. And the summation of our xy is what we got here as 503.
Okay. So does anybody have any question at this point? Or you are not clear of what he has done so far? All right. In the absence of no question, you may continue, please.
So we can see that the summation of our s is equal to 52. The summation of our y, calculating the summation of our y values is equal to 72. The summation of our xy, here we first get the summation of our x, the product of our xy to be 32, 36, 2, 120, multiplying the value of our s to this, and we find the summation to be 503. Our s squared values too are given as this on this line, and we find the sum to be 468. We now take all these values calculated and substitute it to our equation. So from equation 1.0, we have that the summation of our y to be equal to our na plus the summation of our s. And from the table above, we have that the summation of y to be 72, the summation of s to be 62, and we now substitute all those values into our equation 1.0. Here we are trying to determine the straight line coefficients a and b using the norm equation. Here we have the summation of our xy to be 72. We substituting all these values into this equation 1.0. We have it as 72. Here our n is the number of nodes. From the time series data, if you count it, we have it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the number of nodes on the graph of our experimental data. So that's what is given as our n. This is the number of nodes to be equal to 10. So we substitute all those values into our equation 1.0. We now have it as 72 is equal to a plus b plus 62b. And also from equation 2.0, given here, we have it as this summation of our xy is equals to a summation of our s plus b summation of our s squared. And from our table above, we already calculated that the summation of our x squared to be 48, summation of our xy to be 503. Substituting those values into equation 2, we now have it as 503 equals to 62a plus 468b. Now we have to solve for our equation 3 and our equation 3 and equation 4 to be able to get our a and b value. So by direct substitution, from our equation 3.0, we know that our a will now be equal to 72 minus 62b over 10. We now take our a is equal to 72 minus 62b over 10, and we substitute it into equation 4.0, which we have here. So we should now be equal to our 503 equals to 62 times 72 over 62b minus 10 times 62 minus 62b divided by 10 plus 468b. Now solving for b, as you can see, we arrived at our B to be equals to 0.677. Looking at the equation here, we arrive at our B to be equals to 0.677. Here we now take the value of our B, which is equals to 0.377, and substitute it into equation 3.0. Stated there as 72, which is equals to our A plus 62B. So here, substituting our B, which is equals to 0.677 into equation 3.0, we now have it as 72 equals to 10A plus 62B. Substituting our B equals to 0.677, we now have it as 72 equals to 10A plus 0.677 times 62, which we now have it as 10A equals to 30.0.26, and we divide our 10 in both sides. We now have our A to be equals to 3.0026. Now we know we have our least square line equation to be equals to y equals to A plus bs. Here we will be able to derive the value of our A and the value of our B to be equals to our A to be equals to 3.0026 and our B to be equals to 0.677. Substituting those values into our least square line equation, our y is now giving us 3.0226 plus 0.677s. Yeah, now that we have our least square line equation, we can now take our time series data and try to plot the graph to be able to get our straight line equation. So plotting the graph, here we have it as this. Our least line equation giving us y is equal to 3.0226 plus 0.677s. Substituting the value of our s from our time series data, we are able to plot this graph to show a general trend of our data. So I will stop here and my colleague will take on from here. So Mr. James, you can continue, or Prince.
I think Prince, you should be the next person.
So Mr. Prince, you can take on. So I will stop. Hello, Mr. Prince. Mr. James, you can just continue.
Hello? Okay. Let me continue.
So should I stop sharing? So you share from me.
You can stop sharing so I can share my screen.
Okay.
Yeah, there appears to be a feedback from somebody. Like
okay.
A booming sound.
All right. Can you see my screen now?
Yes.
Hello? Okay. All right. Thank you. So I will continue from where my colleague stopped. So I will be talking about another method of interpolation, which is the Lagrange interpolation method. So if we have followed from the beginning, we notice that he has been talking about interpolation, and then different methods that we can use to interpolate certain functions. So one
Mr.
other
James.
method that, okay.
Hello, Mr. James.
Yeah, I can hear you.
Yeah, are you using any earpiece? There's a feedback, or you are charging your phone and using the earpiece at the same time.
Okay,
There's
I'm using
murmuring.
Okay, I'm using earpiece.
And are you charging your phone at the same time?
Let me remove it and use the device. Or is it okay now?
Yeah, that feedback has stopped.
Okay. Apologies.
Okay. Please stop watching football or put yourself in mute. Thank you. You can continue, sir.
All right, thank you. So like I was explaining, Lagrange interpolation is another method that we can use to interpolate functions. And this method was actually developed by a French mathematician known as Lagrange. So Lagrange interpolation is a formula for finding a polynomial that approximates the function f of x. It simply derives an nth degree function that passes through n+1 data points. The f of x is the exact function which only n+1 discrete values are known and used to establish an interpolating or approximating function p of x. So what we are saying here is that we will be given the n+1 data of values will be known to us or will be given to us. Then, of course, for every input, we'll have an output. So the function which we now interpolate or approximate is the p of x. Then the p of x will pass through all the known n+1 interpolation points, also referred to as data points or nodes. We will get a better view of this when we look at it in a graph. So looking at this graph here, our function, which is the known one, is this one that is in black line. If you can see, I'm tracing it through. So that is our f of x. That is, we know this function. Now, the idea of interpolation is what? To approximate or to estimate a function from a given set of data. And so we can see our interpolating function now. This the one in the dashed red line. So that is our interpolating polynomial. So if we also observe, we notice that it passed through all the functions, that is the n+1 data points that we know. So from here, we can see that the interpolation points or nodes are given as, so we have x0, then the output f of x0, x1, f of x1, x2, f of x2, all the way to xn and f of xn. Now we see that this symbol here, which is approximately equal to f0. So this actually is gotten from the approximation theory. So at x0, at this node, our function approximates to f0. And also at this node, our function also approximates to f1. Also at x2, this particular node, our function also approximates to f2. And the interpolating polynomial will pass through all the given points. So if for instance, we have 4 points, the interpolating polynomial we are going to generate will pass through that 4 points. And then with that polynomial, we can now approximate or estimate values in between that bound. So moving forward, we'll now try to develop the Lagrange interpolation formula. Of course, like we have said, what we are doing is interpolation, which is to estimate values from a given set of data. Of course, within a bound. So, and I have already said that the method, one of the methods we can use is the Lagrange method. So for us to derive this method, we'll state that given a set of n+1 data points, which start from x0, x1, all the way to xn, we define a function or some function which is L0, L1, all the way to Ln. And these functions are called cardinal function or the Lagrange basis polynomials. So then there are polynomials of degree n and satisfy the following. So when we estimate the value of x, or we evaluate Li of x, it is equal to this particular symbol, which is a chronicle delta. So I'll explain. The chronicle delta is a form of a delta sign which holds two values. So what does it do? It tells us that when I is equal to j, the function should return 1. And once I is equal to j, the function will return 0. So this is actually a function or a property which we know in mathematics as a local support function. So when we are dealing with the discrete points, that is, if we have x0, x1, all the way to xn, At point 0, if our I is equal to j, we will return 1 j. And at every other node, it becomes 0. And this is actually one of the breakthroughs that Lagrange got in order to establish its own formula. So we'll now look further to establish this L function properly. So we are given that this Li of evaluated at x is actually equal to this sign is called a product of this function here, starting from 0 all the way to n. And also know that our I cannot equal j. The reason is this: if our I equal j at any point in time, for instance, in this first one, maybe at L0, if I equal j, then here will become sj minus sj, which becomes 0. Therefore, our equation becomes undefined. So we'll move on to the expanded form, because like I said, this sign here is just, it tells us that this particular function here is a product. So we are going to multiply it starting from 0 all the way to n. So for the first one, we have x minus s0, x minus s. So this is the expanded form of this particular formula we are seeing here. S minus s0, s minus s1, all the way to x I minus 1, x minus xi plus 1, and all the way to x minus xn. Again, divide by xi. Then if we also follow this formula, so remember that we say that I cannot be j. So if we look at this point that x0, at s0, we cannot have x0 here. Because if we have x0 minus x0, it will now become undefined. So we'll continue, we'll get a better appreciation of the formula when we start using it to actually solve problems. So we'll now try to derive the Lagrange formula proper. So we went through all that problem to derive the Lagrangian basis polynomial, because it's part of the basic thing that we see in our formula. So in general, Pn of x, that the polynomial of n degree that we find, which is the Lagrangian polynomial, is equal to L0 F0 plus L1 F1 plus L2 F2 plus all the way to Ln Fn. So we notice that this is one Lagrangian basis polynomial, or one cardinal function, and all this. So the summation is what we have here. So we can have it all the way to 150, whichever one. So let's just know that we have one for every Lagrangian basis polynomial, we have a function that is being outputted. Now, if we look at the Fi's here, which is the F0 here, is also equal to Yi, and is also a function Fi of x. Why I brought this out is that in certain notes or in the textbooks, they will be identified, they will be written as Fi, that is F0, F1, F2, all the way to Fn. In other textbooks, they can also be written as Y, which is Y0. So you will see them as Y0, Y1, Y2, all the way to Yn. And also some will write it out in full, which is F of or Y of x. So now let's look closely at the L approximated at x. And this is given as x minus s1, then s minus s2, all the way to s minus sn. That is for the first basis, the Lagrangian basis function, or the cardinal function. So the L2, also x minus s0, s minus s2. Now let's let's notice something here. So when we are considering, if we recall that we say that the local support function that we talked about earlier, we say that if we consider the discrete points, that is, for instance, we are considering point x0, at every other node, it will be disregarded. So now, if we are considering it at L0, we will not have x0 at the numerator, but what we now consider, if you are considering L0, we now start considering X0, X0, and all the way to X0 minus Xn. So if we also observe, if we look at L1, on the numerator, we will not have X minus X1. Like that, it continues. At L2, we're not going to have X minus S2 at the numerator, but we have S2 minus all the other nodes continuous. So this is the basic form, pattern that the Lagrangian formula takes. Once you're able to know that if you are considering L0 for the numerator, you will not have X minus S0. Well, what we are now going to use at the denominator is S0 minus all the other nodes. Again, if we start solving problem, we also get a better appreciation of it. So let's consider it one after the other now. So for the first degree polynomial, our Lagrange formula P1 of X. So for a first degree polynomial, we have two data points. That is, we're going to have X0 and X1. We always start with our data points from X0. So we have two data points, and looking at our formula here, we have also that two data point is represented here. So we have L0 F0 plus L1 F1. You remember our general formula was L0 F0 plus L1 F1 all the way to Ln Fn. So because we have two data points, we are stopping at L1 F1. So now our Lagrangian basis, this L0 is given as S minus S1, S0 minus X1. Remember, since we are considering L0, X minus S0 will not be at the top, but it will be, we'll have S0 at the denominator. So likewise, when we are considering the L1, the X minus X1 will not be at the numerator, but X1 will be at the denominator, and then the pattern continues. Similarly, if we look at the second degree, for a second degree polynomial, which is also known as a quadratic polynomial, is a polynomial which have 3, so our data points will be 3. We are going to have X0, X1, and X2. Now, our general Lagrange formula, like we have already seen before, we have L0, F0, L1, F1, all the way to Ln, Fn. So for 3 data points, we will have 1, we have 2, and we have 3. Now, our L0, again, we are not going to have X minus S0 at the numerator, but we will now have X minus S1 and S minus S2. So the pattern continues like that. So now the same thing happens to the third degree. For third degree polynomial, which is the cubic polynomial, we're going to have 4 data points. So we are going to have L0, L1, L2, and L3. Then, of course, we have for every L0, we have the output, which is the F0. Now, again, if we are looking at these formulas, they will look very maybe intimidating, but all these things are going to be numbers. So when we start solving, we're just going to be taking, once we are given our data points, we just pick each data point. For X, we will know our X1, our X0, X2. Then we also know our F0, F1, or whatever we are given. The only thing that we may not know is the X, which is what we are trying to now find. So let's look at an example. So in this example, we are asked to find the linear function P of X that passes through the points 2, 3, and 5, 9 using the Lagrange interpolation formula. So now, immediately we see this problem, we have seen that we have 2 data points. And if we have 2 data points, we have a linear function. So we just go and write our P1, which is the first degree polynomial for Lagrange. P1 of S is equal to, we have 2 data points. So we have L0, F0, L1, F1. From looking at our data point already, we already know that if we look at this box here, this is our F5s. And this is our F0, and this is our F1. So our F0 and F1 is already known. And this is our X0, and this is our X1. So if we write out our form, we'll just, remember, we the only thing we are deriving is the Lagrangian basis polynomial, which are the L's, and we have already taken the pain. So we are now seeing why we took that pain to derive that formula. So for the L0 in a first degree polynomial, we have x minus x1. Remember, x0 will not be at the numerator. Rather, it will be the one that will be repeated as the factor in the denominator. So we have x0, s minus s1, s0 minus s1. So we'll just go to our table, we pick our s0, which is, okay, we'll pick our x1, which is 5, we'll plug it. We'll pick our s0 minus s1 and we'll plug it. So once we solve through and do some basic arithmetics, we end up with our figures. So now if we further simplify, now look at our formula, which is what? L0, F0. So we just, after we have gotten our L, like the Lagrangian, this thing, we just multiply it by our F. So you see it here, multiply this, then also do this. So finally, we're going to have a function. And this, if we look at this equation, this is a linear equation. So it has satisfied our problem. So let's move again to another question. So in this time, we'll try to solve a question that has 3 data points. And a 3 data points, polynomial is a polynomial of degree 2. We just know it that if you have 3 data points, your polynomial is polynomial degree 2. If you have 4 data points, your polynomial is polynomial degree 3, and so on. And so if you have 100 data points, your polynomial is polynomial of degree 99. So here, we'll go back to our Lagrange formula, which we know is just summation of the L and F's. So for 3 data points, we are going to have 3 summations. So we have L0, F0, L1, F1, and L2, F2. Now recall our L's. We have, for when we are considering the L, remember the local support function, the x0 will not be at the numerator. Rather, it will be the factor in the denominator. So, and now, you can also, because some may be trying, we may say, okay, can we memorize this formula? We don't even need to memorize the formula. Once you have already known that you have 3 data points, and you know that you are going to have x0, x1, and s2. So what you just need to do is, you remember, if you are concerned about the L0s, you won't add x minus s0 at the numerator. And then you have x0 minus x1, then minus s2. And that's it. So this pattern, once you're able to get this pattern, you will solve all your Lagrange interpolation problem. So the same thing, we already know our FIs. Our FIs, so F0 here, F1, and F2. Then we take our XIs too. This is X0, X1, and S2. So we plug into our equation. When we solve, we get this equation here. And then we now take our F values, multiply it, and then we do some arithmetics, we end up with this equation. Again, this confirms that it's a quadratic equation, which also further corroborate solves our problem here. Then we now look at another example. In this example, we considered a 3rd degree polynomial. So, but this example is more practical in that we are solving a practical problem. Okay, so it makes no sense if we are finding a formula that is not useful, or maybe it doesn't have a class. So this will also, at the end of this, we'll also see why interpolation is also very important in mathematics and in engineering and sciences. So this table is actually a table of functional values that are generated for which f of x is equal to the natural log of x. So if we press our calculator, the natural log of 0.4 is minus 0.196291. So the same thing, 0.50, a natural log of 0.5. So these are already computed values. So meaning experiments have been, if for instance, you are running a bunch of experiments, you run experiment 1, you have an output. You run experiment 2, you have an output. Experiment 3, you have an output. Experiment 4. Now we are asked to find 0.60. We could just go ahead and run the experiment 2 to get 0.60. But what if this experiment takes maybe a month or 2 months to run? So, but we have already gotten a range, so we can now use this beautiful method that Lagrange has, given us to interpolate or approximate the value for 0.6. So, what do? We go to our, we recall our Lagrange formula for degree 3. We're going to have 1, 2, 3, 4 data points. So it's going to be L0, F0, all the way to L3, F3. Now we put our the basis of our, so this is the L0, this is the L1, and this is the L2, L3. Remember that this is just a summation of all our L's. That is why, so you don't need to always be, you can write the L and then later on join them together, but you can just, put them, lump them together like this. So we now again revert to our table. So in this case, in the last examples we have solved, we first of all solved for the polynomial function, that is the equation. We can as well do that, but here in this case, we're already given the value, the S that we need to find. So in order not to waste time, we can just go ahead and plug in that value for X and then evaluate. So if we see here for in the L0, we have S minus S1, S minus S. So our S is what? 0.6, and our X1 is 0.5. That's what we have here. Again, we have S minus S2. Our S is 0.6, and our S2 0.7. Like that, and we continue. And remember, there will be no, since we are considering the L0, there will be no X minus S0 at the numerator. But if we go to the denominator, it will become the factor there, which is 0.4. That's our S0. That is S0 minus S1, S0 minus S2, S0 minus S3. So once we plug in all this, now look at our FIs. Our FIs, that is F0, F1, F2, and F3. These are the values. We just put it here and multiply. So when we do all the arithmetics, plus and minus and division, we are going to have our P 0.6 will be approximately equal to minus 0.509976. Now, if we use our calculator, for that is, if for instance we are doing the actual experiment, so if this were like experiments which take days or hours.
Yeah, hello.
We can't hear you.
Okay, I thought as much. Mr. James Agba.
Yes, sir.
Okay, we can hear you now.
Oh, okay. I apologize. I think it's my network.
Okay.
So, like I said, if we after plugging all these values and we arrive at our figure, we can also confirm by pressing our calculator, and our calculator gives us this value, and this is the same thing, approximately equal to this. So this is the beauty of interpolation. You can get a result of something, even though you may not necessarily carry out that particular experiment. So we move on to Newton's interpolation method. Again, this is another method of polynomial interpolation. So we have talked about several methods, and I just talked about Lagrange. So this is another method that we also use to find a polynomial that we can use to approximate a function. So Newton polynomial is an interpolation polynomial for a given set of data points, which, like we have said earlier, it is sometimes called Newton's divided differences interpolation polynomial because the coefficients of the polynomial are calculated using Newton's divided differences method. So we'll get a hang of this as we move on. Now, why do we even need
Mr. James, sir?
Yes, sir.
Please, can you tell your people to excuse a bit? You can hear their voices respectfully, sir.
Okay.
So when is back, you may continue.
Okay, I'm back. Apologies for the.
It's no problem. I understand that you're at home.
All right, sir. Thank you, sir. So, like I was saying regarding the Newton's method. Now, when we were solving for the Lagrange method, we noticed that for every degree polynomial that we are solving, our L's, that the Lagrangian functions, were changing. For instance, in the first degree polynomial, our L0 was a function that we got. In the second degree, L0 was also different. In the third degree, L0 was also different. Likewise, L1, L2, and all the way. So that means if we are going to solve all the way to L100, we are going to have different values. So we'll solve for 1, we'll solve for 2, we'll solve for 3, all the way to that 100. So it will be computationally very tedious and also prone to error. And that was where the Newton's method came to rescue. So Newton's method, what did it do? It takes, if you solve for one polynomial, you can take what you have gotten in the first polynomial and use it in the second one. If you solve for the second one, you can also use what you solve in the second one and use it in the third one. So if we look at it here, the general form of the Newton's polynomial have P1 of x. That's for the first degree polynomial. P1 of x is equal to f0 plus s minus s0 multiplied by this function here, which is, this function is known or called the divided difference. And this is the first divided difference of Newton interpolation. And the formula, it actually has a formula, and that formula is f1 minus f0, x1 minus s0. Now, I think we will be familiar with this, our f minus f0. If we go back to our, if we have our, maybe the xx, if we have two data points, for instance, the first data point is f, that is x0, and then this s1, and the corresponding output is our f. So this will also be figures. Okay, so we won't be intimidated by these strange looking symbols. So then for the second degree, we have, if you look at it, f0 plus s1, f0 plus s minus s0, then multiply by f. This is the first degree now added to an extra time. So, and this is the extra term now, because we are considering the second degree, and we recall our second degree, we have 3 data points. We have s0, x1, and s2. Now, to find this is called the second divided difference. To also evaluate that second divided difference, we now also use it in terms of the first divided difference. So again, these things will be figures. They will just be numbers. We just need to plug them in, and then we evaluate and get our values. But what we just need to remember is, once we are in any degree, if we are in degree 1, our data point is 2. If we're in degree 3, our data point is 3. And our data point always starts at S0. So if for 2 data point, S0, S1, for 3, S0, S1, S2, and so on and so forth. So now we try to generalize it so that, but I always prefer if we are using it one by one. So, but this is the generalized form. So this is the first polynomial of the Newton's method. Then we now continue, second polynomial, third polynomial. For that is if you have other, maybe if you have 5 polynomials, for instance, it continues. And then this is the extra term. If we look at this is just the xn. If it's a second degree, to stop here. So second degree will be 3 data points. x3. So then this is the divided difference. Again, this is also the generalized form of the divided difference. And again, for us to get the better appreciation, we also need to solve problem, because if we don't solve problem, we won't get to understand it. But I also want, let's look at this table. This table is meant to make our work very easy. It is called the divided difference table. So now, looking at this table, this x and f, these are our the xi's and the fi's. We have, for this table now is for 1, 2, 3. This is for a third degree polynomial. So that is 4 data points. So we have S0, S1, S2, and S3. For us to now find this table, what do we do? For the first divided difference, we just take the difference between the F1 minus F0, divide by S1 minus S0. We'll get our value. Will be here. Then the same thing will continue. F2 minus F1, X2 minus X1. The next, F3 minus F2, S3 minus S2. So at the end, we are going to have a number. We'll have a number here, we'll have a number here, we'll have a number here. So that, remember I said that we are, for the second divided differences, we use it in, we find it in terms of the first divided difference. So the number we have here, we also multiply this minus this, which is what we have had here. Look at it. F S1 S2 minus F S0 S1, and divided by the difference between them. So this is the same thing we do here, and then all the way. So we are going to do this table together, so we also get a better appreciation of it. So in this example, where we solve, so we are asked, given the data below, we are asked to compute for the f of 9.2 using the Newton's divided difference method. So we have our xi's and our fi's. So s0 is 8, s1, s2, and then x3. The same thing, f0, f1, f2, and then f3. So, of course, the first thing we should do, we write our formula, which we, from our general formula that we have already known, we know that the first polynomial, that is f0 plus s minus s0, and then multiply by f, because of the first degree, we have 2 data points, s0, x1. We'll add the next polynomial, x minus s0, s minus s1. In this case, we are now having 3 data point, which is the second degree. Now, if we look closely, very well, we'll see that these signs, these functions here are our divided differences. So this is the first divided difference, this is the second divided difference, and this is the third divided difference. If we go back to our table, we can see how we found it. The first one, we just do f1 minus f0, s1 minus s0, we get a figure. We get a figure. Then what the figures we get, we minus it again. So this will just end up becoming numbers and numbers until we get the last number. So we now develop our divided difference table. So again, we have our xi's and then the fi's. So the first divided difference, like we have said, is just difference between the f1 minus f0. So 2.1927225 minus 2.079442 divide by 9 minus 8. If we press it, we are going to have this. So we got this. The same thing we do here, 2.251292 minus 2.1297225. So, and then 9.5 minus 9.0. So we will get this figure. The same thing we do here, 2.397895 minus 2.25 1292, again divide by 11 minus 9.5. So once we have gotten at this point, at this level, if you recall, I said those functions we were seeing then, they are all going to be numbers. So we will now take this number again to get the second divided difference. We'll take 0.108134 minus this one. Then divided by the distance between them, which is now 9.5 minus 8.0. So we'll get this. The same thing, we'll take the difference between 0.097735 minus 0.108134, divide by the distance between them, which in this case is 11 and 9. We'll get this. Now we are at this level. To get this level, what do? We take this particular figure minus 0.0052 minus this. So we are going to minus this from this. Of course, the sign will change, so it will only add. Then divide by the distance between them. The distance between them in this case is 11 and 8. So when we divide it, we end up having this figure. So now, why did we go through this table? It's just for us to get our first, second, and third divided difference. And once we get it, if we go back, look at our formula, it's just for us to plug in. In the first part, this is our first divided difference, second divided difference, third divided difference. Then on this side, I have already plugged it in. First divided difference, just our figure here, we'll put it there. Second divided difference, we'll take our figure here, we'll put it. Third divided, we'll take our figure and put. Now, our F0, we already know, which is this. Remember, these are our Fi's, and our F starts from F0, F1. So take our F0 and also put. So we are only left with the X, which is what we are now asked to compute, which is the 9.2. So the same thing, we plug in the 9.2 minus this, we'll do the computation, and then finally we'll end up with 2.219208. Again, if we use our calculator and press the natural log of 9.2, we are going to end up having 2.21920348405, which also is approximately equal to what we have here. So maybe this is where I will stop. So the next person will now talk about another method of interpolation, which is the Hermite interpolation. If Prince is on, you can continue while I stop my own presentation.
Okay. Good afternoon, everyone.
Yes, good afternoon.
Okay, sorry, so I'm trying to share, but I'm not a host. So.
Okay. That means you didn't raise up your hand when I asked you to.
Yeah, okay, sorry. I had network issues, so I had to leave the chat.
Yes, you are not a host. You may try to share.
Okay. Okay, good. I don't know if you can see my screen here.
Yeah, are you using your phone?
Yes, sir.
Yeah, can you slant it the other way?
Okay.
Okay, so you can go back to your slide.
Okay, sir. Today I'm talking on Hermite interpolating.
You're not charging your phone. Your power is quite low.
Today I'm talking on Hermite interpolating polynomials. So I'll give a brief definition on it before I start. The Hermite interpolation computes a polynomial of degree less than mn such that the polynomial and its n-1 first derivatives have the same values at n given points as a given function and its m-1 derivatives. So the Hermite method of interpretation is closely related to the Newton's interpretation method in that both are derived from the calculation of divided differences. However, there are other methods for computing a Hermite interpolating polynomial. One can use linear algebra by taking the coefficients of the interpolating polynomials as unknowns and writing a linear equation, the constraints that, and writing as linear equations the constraints that the interpolating polynomials must satisfy. So here we have Hermite interpretation consists of computing a polynomial of degree as low as possible that matches an unknown function, both in observed value and the observed value of its first derivative. This means that n+1 values must be known. The resulting polynomial has a degree less than n+1. So we have this figure here which shows the x and y values up to n-1, and then at the bottom here we have the x and y values into raised to power m. So we'll then define some elements. The elements denoted by the letters are defined, but this figure, we'll go back to it later. I would just like to move ahead to the formula. This is the formula for the Hermite interpretation, which says that Hn into x equals to the summation of f into xk, hk into bracket x plus f prime into bracket xk, hk into bracket x, or bracket. So then we now have a divided difference table for the Hermite interpretation, the final formula. So just as my other colleague had defined in the Newton formula, in the Newton method of solving interpretations, we have the divided differences table. So here is the formula in which it is solved, basically. So we have the constant, which is the k here should stand for the x, and while the xk is the y values. So we have 1, 1, 2, 2, while the x values is a, b, and b. So the let's just go to an example. So we consider the function. We consider the function of x, where x raised to power 8 plus 1, evaluating the function and its first derivatives at x that equals to -1, 0, and 1. Therefore, we obtain the following data. So in this table now, we have when x is -1, the function of x is 2. When it's 0, the function is 1, and when it's 1, the function is 2. So the first derivative from this for when x is -1 is -8, while when x is 0, it's 0 too, and when it's 1, it's 8. For the second derivative, we have when x is -1, then the second derivative is 56. When x is 0, it's 0, and when x is 1, it's also 56. So now we'll go to the divided differences table. So since we have two derivatives, to work with, we construct the set wherein we have -1, -1, and -1, 0, 0, 0, and 1, 1, 1. Our divided differences table is then this. So when we do the whole calculation, when we solve everything using this formula here, when we calculate all the figures using this formula here, we'll be able to arrive to this, which gives us the first, second, and third divided differences. And then the generated polynomial will give us that p into x is equals to 2 minus 8 into x plus 1 plus 28x plus 28 into bracket x plus 1 square minus 21 into bracket x plus 1 cube plus 15x into bracket x plus 1 cube minus 10x square into bracket x plus 1 cube plus 4x cube into bracket x plus 1 cube minus 1x cube into bracket x plus 1 all cube into bracket x minus 1 plus x cube into bracket x plus 1 cube into bracket x minus 1 square. So all this, the whole formula then gives us x raised to power 8 plus 1. So that's the end of, that's how we do the termite interpolation method. So I don't know if any of my group members have any other thing to say. Maybe James.
All right, thank you, all the group members, for your presentation. Do we have any questions for the group members? Any questions, please? So I want to assume that you all understand what has been discussed today. Well, I think some of you are having issues with your batteries. I intended that we have two set of presentations today because you guys refused to attend classes the last week. So to that extent, I was hoping that we're going to do two presentations today, but we know what is obtainable in the country. I've been running generator for some hours now just to get this class underway. So I don't know if okay, James Agba. Yeah, James Agba, your hand is raised up. What is the problem? Mr. James Agba.
Yes, sir. No, it was when you asked that we indicate for those that are presenting. Let me drop it.
Okay. All right. So let me quickly take the attendance while we look at the next thing to do. So who is Odenride Moses? Is he present?
Present, sir. Yes, sir.
Yeah. Are you supposed to present the next? Huh?
No, sir. No, sir. Our group is the last group, sir. Group 7.
Okay, I can Rolabu. Lola de Sire. Oh, you are the one who presented. Okay.
Yes, sir.
Mba Mena Emmanuel.
Present, sir.
Ezekiel Tobi Bukumi. Ezekiel Tobi Bukumi. Elegbede Bankole.
Present, sir.
Were you fighting with somebody?
No. No.
Mbingu Samuel Chika.
Present, sir. We are the one presenting next, sir.
Oh, your voice is quite friendly. Abdul Rahim Miriam Bukola.
Present, sir.
Okay. Agba James Aguzie.
Yeah, present, sir.
Namdi Chukwuemeka.
Present,
Namdi.
sir.
President.
Present, sir. Present, sir.
Stop shouting now.
I'm flagging, sir.
Osagiduwa Ebenezer. Did I correct it? Osagiduwa Ebenezer. I don't know if I'm correct. Is that fellow around? Okay, thanks. Shoton Cindy.
I can see Ebenezer on the call, but I don't know why he's not responding.
I've marked him absent. Shoton Cindy.
Present, sir.
Okay. Akinwande Oluwatobiloba. Akinwande. Absent. Oluwasusi Victor. Oluwasusi Victor. Okay. Absent. Yeah, I can see somebody raising up his hand. Come. Yeah, who is raising up his hand? Somebody is raising up. Yeah. Continue. Where did I stop? Okay, there's Lawal Farouk.
Present, sir.
Okay. Oladipupo Oluwade Jeremiah. That guy refused to present. I don't know why. He has constantly been absent. Musliuddin Abdul Rahman.
Present, sir.
Okay. Abdul Salam Miriam.
Present, sir.
What's wrong? Is it
We are
Ramadan?
No, we are running on generator too, sir.
Oh, that's why you're angry.
Yes.
Oh, sorry about that. Falco Radio Lumide.
Present, sir.
Okay. Ogbaji Michael. Ogbaji, is he around? No. Okay. Uluka Prince.
Present, sir.
Yeah, why you have not attended any class? Why?
I've been dealing with some family issues since, that's why.
Oh, sorry about that.
Okay.
Jebutu Mo Refill Luwas.
Present, sir.
Okay.
Present.
Moshood Aliu. Huh? Okay, absent. All right. For those of you who are protesting that you are running generator, I think I should be the one complaining now. Yeah, so grading, Akin Rolabu Lolade Busayo. What can we grade him to be? Huh?
Hello, sir.
You just presented today, right?
Yes, Akinolabu.
Yes. Maybe we sing good afternoon. Yeah, please, can you send in his grade on the chat group? Then the other fellow is Agba James Aguzie.
Yes, sir. I'm present, sir.
Wait, Sam. Mariam to everyone. Okay, who is Ebenezer?
I'm present, sir. I had to receive a call. I left the class.
Ebenezer. Ebenezer what?
Usagiotua.
Eh?
Usagiotua.
I've marked you absent already.
Oh, I was present. At that time when you were calling, a call came in, so I had to receive the call.
But that's not good enough now as a
I'm
student.
sorry, sir. It was not at that point that the call came in. I'm sorry, sir.
I think Your village people after you, Abi. All right. I've verified that.
Maybe his
Thank you,
gen
sir.
went off too.
You people are trying to blackmail me to cancel the next class, Abi. Okay. All right. Well, to be sincere, I feel like I'm quite impressed by some of your presentations anyways. So I'm having a very biased mind towards most your class, especially. When I say bias, I mean you guys make things look quite easy, but you are not disciplined with time. And I don't really take it lightly when people don't show up early. I've been on since uh, is it 12:47, just to make sure that okay, I set up everything. And I've been running generator even before then. My generator got spoiled. I had to drive out to go and get what I'm supposed to use to fix it. I did just to meet up the class. So if I ran through all odds just to honor the time I've given you, I think you guys should also do better by coming to class early. I don't know, but I'm not quite happy with your lack of being punctual. Yeah, and I feel that that's not good enough for postgraduate students. So I hope that will change going forward. You haven't said that. How many of you want us to push up the next presentation to next week? You could just raise up your hand by a simple vote. So we take the majority. If you want us to push the next presentation to next week, please raise up your hand.
Next week are supposed to win, sir.
As opposed to today. So we have not broken any tie. So I think the tie just got broken. So 12 people voted for us to move to next class. Now, for those of you who don't want us to move to the next class, I hope you will not be offended at this. Okay, somebody has dropped his hand. So 11, 10, 12, oh boy. You guys are not smiling. Well, I think the only reason why I'm going to shift it is because of the Ramadan fast. And I'm sure that most of those guys who are doing Ramadan, they are quite tired as we speak. So we should also give them a break. We should have done it last week. And this week, you will just be doing little works. But well, that's how God we have it. And I wish you happy Ramadan as you, and may God accept it as an act of worship for all of you. Having said that, I hope those who will present next week will not be offended, and you will bear with us given the circumstantial evidence that we have presented. 1, because of power supply. 2, because of fast. Then 3, I don't think you may have the steam power to concentrate any further. So I've seen the scores you have all sent in, and I hope by next week you guys will come early. Or are you still, will you be tired next week, or do we move it forward or something? Do we move it? Okay, next week is sacrosanct. That means we're going to meet next week, right?
Yes, sir.
Okay, so
Yes,
meet
sir.
next week. And those of you who are going to be on Ramadan, please, during the early morning food, please eat enough so that you have strength to cross 1 to 3. I know you are supposed to be sleeping now, but don't worry. God will reward you abundantly. Mr. Laddie, your stuff is making woo, woo, woo. Okay, so I've made you eat. Okay. All right, so please have a pleasant weekend, and thank you for the presentation. For those who presented today, please let's have your slides on the chat group, some of your solved problems that we requested for. Then for those of you who have presented before now, I want you to send me the slides of what you have done on my private mail. That's femialamu@gmail.com, all in lower cases. femialamu@gmail.com, all in lower cases. And I want it before 5 o'clock today. So please have a pleasant day. I want us to quickly finish this so that you're ready, you know the range of questions that you'll be looking at for your exams. Well, I don't see any of you having, well, let me not be categorical. For those of you who have constantly attended the classes, I want to assure you categorically because I'm also probably thinking that the other okay, I think my network is breaking, but I think you can still hear me. I also probably other lecturers would have also observed that same traits in you. The worst set of postgraduate students we had were MSc last session. Yeah, but I think you guys are changing that narrative to a large extent. So I hope that we get things positive, and we hope that you guys will come into your master's program and you still repeat the same feats that you are going by. You guys are doing a wonderful work, and no lecturer in his right mind will want to do anything to upset your grades, as it were. So please have a pleasant week or weekend and week. All right, so we'll meet next week. God willing.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Wait, so I'm hearing Mr. Laddie said he has not missed my class. Let me see your attendance, please. Mr. Laddie. What's your full name, please? Laddie. Mr. Laddie, what's your full name? He has suddenly gone quiet. I can't see any Laddie on my work. Mr. Laddie.
I don't think it's Mr. Laddie. Maybe it's
Somebody wrote that he
he
has not missed the class. So.
That looks like Miriam. It's not Laddie. Maybe she's using a different name.
No, there is a Oladipupo, Jeremiah. I think that's his
It's
full name.
Oladipupo Jeremiah Oluwakowade. Olukowade, something like that.
Okay, Oladipupo Olukowade. Okay, let me see. Oladipupo Olukowade. Is that the surname? Oladipupo. You said you have not missed my class. You didn't present now when your guys were presenting. So you had the 0. And you have missed 1, 2, 3. You are in class and I've marked you absent today. See your problems. So you didn't present when your guys were presenting. So you had 0. Who is that one shouting? Yeah, so let's not waste other people's time. I'm always in class, sir. Well, I don't know about that, but that's what that's what the record shows anyways. All right, so gentlemen and ladies and gentlemen, please have a pleasant week ahead and weekend.
Yes, sir. Bye.
Bye.